Okay, so Chem 111, this is chapter 8, which discusses the periodic relationships among the elements. And we can get started right away by talking about the word periodic. What does that mean? Periodic means that something repeats, Periodicity is another word that we use to describe relationships in the periodic table. And what we're going to see is that we're going to see chemical behavior repeating on in the elements of the periodic table. So they're not just organized randomly. The elements in the periodic table are organized in a thoughtful and useful way that helps us predict how elements are going to react. And you have this funny little cartoon up here on the upper right hand side of the slide that says, "This is how Dmitry Mendeleev completed the first periodic table." Well, Dmitry Mendeleev is a Russian scientist, and he is sort of the godfather of the periodic table, so to speak. And I'm going to talk about how he developed the initial periodic table. But first, let's take a look and discuss, when the elements were discovered. Because as you can imagine, it took a long time to discover all of the elements on the periodic table. If you look at ancient elements, these are things that are, highlighted in gray. These are elements like iron, copper, silver, gold, carbon, sulfur, tin, and lead, gold and silver, of course. These have been known for a long time. But you can see that many of the elements are kind of highlighted in purple here were discovered between the mid 1700s and mid 1800s. And also, most of the elements that come later in the periodic table weren't discovered until well into the 20th century. And again, it took a lot of people a long time to discover all of these elements and to also develop the periodic table so that we can use it to help us predict the behavior of the elements that are in it. Now, just as far as history is concerned, one of the first proposals in terms of how we might arrange the elements in the periodic table was put forth by an English scientist named John Newland. So John Newland's a picture of him here at the top. And what he noticed is that when you arrange the elements in order of their atomic masses, he found that every 8 elements had similar properties, just like the notes on a piano or a musical instrument. If you've ever heard of an octave, we know that the notes repeat every 8 notes. And so he called that the law of octaves. But the problem with that proposal is that it didn't work past the 20th element. It kind of failed after calcium. And so there were some serious problems with that. And, we might laugh at that now, but at the time, some people took it seriously, even though it didn't really, that theory didn't really get off the ground, okay? Now, Dmitry Mendeleev, he is sort of the godfather, as I said, of the periodic table. It says here he grouped the elements together more accurately according to their properties and made possible a prediction of elements not yet discovered. And so if you look at the periodic table and you look at the atomic masses of the elements on that periodic table, you go from hydrogen, which has an atomic mass of around 1 gram per mole, to helium, which has an atomic mass of 4 grams per mole, to lithium, which is around 6.9 grams per mole, so on and so forth. It might be a knee-jerk reaction to think, hey, the elements that are in this periodic table that Mr. D, they are organized in terms of their atomic masses. Okay, they're organized in terms of their atomic masses. But in fact, that's not true. And I'll explain to you, or I'll show you why they aren't. Okay, if you compare the atomic mass of argon, which is around 39.95 grams per mole, and you compare that with the molar mass of potassium, which is 39.10 grams per mole. Potassium has a lower molar mass than argon. And so the elements are, in fact, not organized in terms of their molar masses or their atomic masses. So what Mendeleev did is that he made kind of 3x5 cards. Okay, he took a 3x5 card or maybe some kind of card. I don't know. It doesn't matter if it's a 3x5 card. And what he did is he wrote down the name of the element. So let's say you're talking about carbon, and then he would write down, some of the properties that he knew about carbon. Okay, and then he would do that for all of the elements that he knew of. And he would lay them down on a table, and he kept, kind of playing with them and trying to organize them and find different ways to organize them. And so the first periodic table published was published by Mendeleev, and it was pretty close to what we have now. So again, he didn't organize these elements in terms of their masses. He organized them in terms of what? Their properties. And he saw that their properties were repeating. Let me give you an example. I'm going to back up to my periodic table again. If we look at aluminum, and this example is, outlined clearly in our textbook. Okay, so if you want to know a little bit more about what I'm talking about now, this example, it's covered in our textbook. So Mendeleev knew of the element aluminum. Okay, he knew its molar mass, he knew its boiling point, he knew its density, and even though gallium had not been discovered, because of the repeating patterns that he saw in his crude periodic table, or I shouldn't say crude, but his periodic table that was incomplete, he was able to predict the properties of gallium just based off of his initial periodic table. So even though gallium wasn't discovered until 4 years after Mendeleev published his periodic table, he was able to predict the density of gallium, the molar mass of gallium, and he was also able to predict its appearance and its reactivity, and he did a pretty darn good job of it. And so he was really onto something with organizing the periodic table in terms of the reactivity of the elements and not their molar masses. A little bit more about the whole thing about not organizing the elements in terms of their molar masses, because even though Mendeleev did have the elements organized according to their reactivity, he didn't know about protons, electrons, and neutrons, right? But later on, we see that Henry Moseley determined the atomic number of many elements by bombarding them with high-energy electrons. And what he found, the frequency of electromagnetic radiation that was given off when he bombarded these elements with high-energy electrons, the square root of that frequency was directly proportional to the atomic number. Okay, so the atomic number. And so again, this is more evidence that for organizing the periodic table or organizing the elements in terms of their atomic numbers rather than their atomic masses. Well, if we look at a periodic table that has all of the electron configurations of the elements, shown in here, and you can see that it only shows the outer electrons. It doesn't show the full electron configurations, which we looked at during the last lecture. You're wondering, why would somebody make a periodic table and put, valence electrons? For example, if you look at, let's say, potassium. Potassium has one valence electron, right? It's the 4s1 electron, because if we think about the electron configuration of potassium, the noble gas that precedes potassium is argon, and that's the core electrons of potassium. And then we have argon, and then we have 4s1. Let's look at another example, and I'm just picking them here at random. Let's look at chlorine. Okay, chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons, right? You see 3s2, 3p5, so 2 plus 5 gives me 7. What's the electron configuration of chlorine? Well, the noble gas that precedes chlorine is neon. So I put neon 3s2, 3p5. Now, the reason why it's so pertinent to have a periodic table where we have the valence electrons shown is because chemical reactivity, generally speaking, comes from the valence electrons, okay? When we're talking about, all these different reactions that we look at and study in chemistry, it's valence electrons are the ones that we want to focus on. And so that's why it's imperative that you understand what valence electrons are, okay? Now, something else that's very important in the periodic table is group number, okay? If you look at the horizontal, groupings on the periodic table, right? If you look at this horizontal grouping and this horizontal grouping, so on and so forth, those are called the periods on the periodic table. So we would say over here, these are periods. Okay, so we have period 1, 2, 3, 4, so on and so forth. Now, in terms of the vertical columns, okay, the vertical columns that go like this, okay, we call these the groups. Sometimes these are called families. I never learned that until I immigrated to the States. I always called it the groups, but they call it families. And the reason why we call them families is because oftentimes people who are from the same family resemble each other. And that's what we're getting at by calling these vertical columns families, because let's say you look at the elements that are in group 1A, you're going to find that they react similarly. Not identically, but they do react similarly. Why is that? The reason why is because they all have the same number of valence electrons, right? They all have an outer configuration of NS1, right? Look, we have 1s1, 2s1, 3s1, 4s1, so on and so forth. If you look at group 2A, they all have an outer electron configuration of NS2, right? 2s2, 3s2, 4s2, 5s2, so on and so forth. Look at even group 3. So I'm referring to the Roman numerals here. So if you look at group 3 or 3b, and I'll discuss that in a second, you see here in group 3b or 3, whatever you want to call it, they all have the same electron configuration, right? They all have NS2. So they have NS2, and then they have N minus 1, D1, like that. Okay. Now, without me, spending all this time to go over all of them, for example, if you come over to group 7A or group 17, this is what we call the halogens. You can see that they all have NS2, NP5, so on and so forth. And again, you can see that information in these electron configurations that are all shown for these groups. There are a few things that I want you to be aware of about the groups and the periods in the periodic table, mainly the groups. So let's cover some of that right now. The first thing is that the elements that are in group 1A, okay, group 1A, maybe I'll just write it down here. We call group 1A the alkali metals. Okay, group 2A, we call this the alkaline earths. Group 7A over here, we call this group the halogens. So group 7A, we call that the halogens. And the last group that you need to know the name of is group 8A, which is the very last group in the periodic table. We call that the noble gases. So the noble gases. Another interesting one, just to put this bug in your ear, is the group that has copper, silver, and gold in it. They call those sometimes the coinage metals. So if you've ever heard of the coinage metals, that's what's meant by that. Anyhow, again, the names of the families or groups that you need to be aware of are groups 1A, 2A, 7A, and 8A. Now, you probably noticed that there's two different numbering systems for these groups or families in the periodic table. There's the system that uses numbers and letters, and then there's also the system that just uses Arabic numbers, going from 1, 2, 3, 4, 5, all the way to 18. Now, I think the scientific community is trying to move towards just using the 1 to 18 numbering system because it is simpler. However, old habits die hard in the scientific community. And so when we use the A's, the reason that the A's and the B's can be kind of powerful is because anything that's from an A group, okay, so if you're from an A group, we'll write that here, A group, we call those representative elements. Representative elements. Okay, and then anything that's in group B, we call those the transition metals. So B group, we call that the transition metals. Okay, and if you read more detail about this in the book, there's a little exception there, and that's group 2B, which is technically not a transition metal. But if you call group A the representative elements and group B the transition metals, that's close enough for our class. Anyway, let's talk a little bit more about the classification of the elements, okay? So here it is shown on a slide. So groups 1A, 2A, 3A, 4A, 5A, 6A, and 7A, we call these the representative elements. Group 8A, the noble gases, then we have the transition metals. Group 2B is kind of a special group all unto its own. And then down here at the bottom, this is what I wanted to get to, is these two groups that are, yes, these two, not these two groups, these two rows down here going from 58 to 71 and 90 to 103. These are called the lanthanides and actinides, respectively. So, you need to know your way around the periodic table a little bit. And with all that information in mind and borrowing from some of what we looked at during our last lecture, let's see if we can solve a problem which involves the periodic table. So I'll have to refer back to the last slide. It says here, an atom of a certain element has 15 electrons. Without consulting a periodic table, answer the following questions. What's the ground state electron configuration of the element? Well, if we have 15 electrons, okay, we've got 15 electrons, no matter what, whenever we're doing an electron configuration, it always has to start with 1s2. Now I've accounted for 2 electrons in this element. I haven't accounted for the 13 other ones, so I keep going. I say 2s2, 2p6. Now I've accounted for 1, 2, 3, 4, 4 plus 6, so a total of 10 electrons. Can anybody tell me what comes after 2p6 without looking at a periodic table? There's no such thing as 2d electrons. What would come after? No, it wouldn't be a 3d. So if we go to 3, the next principal quantum number, we're going to have to start with 3s. Exactly, right? Because we're going to have to go spd, right? So we're going to have 3s2. That accounts for 12. And then I'm going to go to 3p, and I need 3 more. So I'll put 3p3. And that is going to be the electron configuration of this element. It says here, how should this element be classified? Well, without consulting a periodic table, you know that the last electron is put in a p orbital, right? And if it's in a p orbital, remember that the s and p orbitals were found in as the outer orbital. I should say the s and the p orbitals hold the valence electrons for the representative elements, and so this element would be a representative element. So representative, and then the next part says, is this element diamagnetic or paramagnetic? Remember that when it's diamagnetic, it's not attracted to a magnetic field, okay? And if something is paramagnetic, it means attracted to a magnetic field. And the reason why something would be paramagnetic is because it has unpaired electrons. So unpaired electrons. And over here, when something's diamagnetic, not only is it not attracted to a magnetic field, it's going to be slightly repelled by the magnetic field. And so all of its electrons are going to be paired up like that. Well, let's look at the valence electrons. And the valence electrons in this element are going to be those electrons with the highest principal quantum number, which is 3. And so we have a 3s orbital, and we have 3p orbitals. In the 3s orbital, I have 1, 2 electrons. In the 3p orbital, I have 3 electrons, and I'm going to put them in there according to Hund's rule, right? I have to have the maximum number of electrons with parallel spin. So 1, 2, 3, like that, right? Remember Hund's rule or the bus rule? They're all going to take an individual seat until there's no individual seats left. And so since we have unpaired electrons, right, these are unpaired electrons, this element must be paramagnetic, right, because it has unpaired electrons. All right. Now, if you're wondering, how would I know? Obviously, you're always going to have a periodic table on your exam. But I think it's a good idea to get enough practice in so that you're able to predict at least a little bit of electron configurations, maybe the first 20 or maybe the first 36 elements or something like that. Okay, well, let's talk about some representative electron configurations of cations and anions. Earlier on, when we looked at nomenclature in this class, we talked about sodium cations, calcium, cations, aluminum cation, so on and so forth. Well, how do we know that, or how could we predict that sodium is always going to form a +1 cation, right? How can we never see this in chemistry? Why do we never see that in chemistry? Well, there's a good reason for that, okay? Why does sodium always form that +1 charge? Why does calcium always form a +2 charge? Why does aluminum always form a +3 charge? There's really good reason for that, and the reason is shown right here. Atoms tend to lose electrons, so that the atoms lose electrons so that the cation has a noble gas outer electron configuration. Look, let me put it to you this way. All atoms have an identity crisis. Now, what you see on this slide, you can see that every example that's shown in this slide is their only representative elements. And the reason why is because when it comes to transition metals, it gets a little bit trickier to predict the charge of the cations formed from transition metals. But let me just go over it with you quickly. The first thing is that metals, you notice that sodium is a metal, calcium is a metal, and aluminum is a metal. Metals tend to lose electrons. If you look at the bottom of the slide, it says atoms gain electrons so that the anion has a noble gas electron configuration. Here are some examples. We have hydrogen, fluorine, oxygen, and nitrogen. Well, what kind of charges do we see for hydrogen? Well, hydrogen can be a proton, H+, but it can also be a hydride, this ion here, which would have an electron configuration of 1s2. Hey, what do you know? That's the same electron configuration of helium. Fluorine always takes on 1 electron to form fluoride. What do you know? When it gains an extra electron, it has the same electron configuration as a noble gas, and we see that with oxygen and nitrogen as well. Let me back up and show you, or let me go forward and explain this to you, okay? All of the elements that are in group 1A always form +1 charges. The elements that are in group 2A, they like to form +2 charges. I'm getting ahead here in my mind, okay? The transition metals, those are a little bit more difficult to predict, okay? A little more difficult. But when we get to group 3A, the elements like to take on a +3 charge. Also, group 4A, a little more tricky to predict. I'm going to go all the way over to group 7A. Group 7A, the elements, they are always like to have a -1 charge. In group 6A, they like to have a -2 charge. And in group 7, they like to have a -3 charge. Now, you need to be fully aware of all these charges that I've written above these groups, 1A, 2A, 3A, 5A, 6A, and 7A. If you're wondering, like, how am I gonna remember that? Well, it works like this. Elements have an identity crisis, okay? They are going to gain or lose electrons so that they can have the same number of electrons as the nearest noble gas. Notice I didn't say any noble gas, the nearest noble gas. Take, for example, potassium, okay? If we look at potassium, what's the nearest noble gas to potassium? The answer is argon, right? If you back up 1, right? If you back up 1, you go from 19 to 18. When krypton loses 1 electron, it goes from having 19 electrons to 18 electrons. Then it has the same number of electrons as a noble gas. We call that being isoelectronic. Okay, when 2 ions, or an element and an ion, have the same number of valence electrons, or the same number of electrons, I should say. Okay, what about calcium? What's the closest noble gas to calcium? Look, if it backs up 1, 2, it's going to have the same number of electrons as argon. So that's why calcium and elements that are in group 2A like to lose 2 electrons. Let's look at aluminum. Why do we usually see aluminum as having a 3+ charge? There's a good reason for that, because if aluminum loses 1, 2, 3 electrons, it'll have the same number of electrons as neon. Don't be fooled by thinking, okay, if I go this way, if I go towards argon, it would have to gain 1, 2, 3, 4, 5, right? Then it would have to be Al5-. Remember, they're going to have the same number of electrons as the nearest noble gas, okay? Not the noble gas that follows them or precedes them. It's just the nearest noble gas. Now let's take a look at some nonmetals, like, for example, chlorine. Why does chlorine always have a charge of -1 when it gains an electron? Because it likes to have the same number of electrons as the nearest noble gas. You see the same thing applies for sulfur. Why is sulfur always S2-? because if it gains 1, 2 electrons, it becomes isoelectronic with argon. Why is phosphorus always P3 minus? Because if it gains 1, 2, 3 electrons, it becomes isoelectronic with a noble gas. All right, there we go. So again, you need to be fully aware of these charges. Let's try a problem here that involves valence electrons of an element with a charge. And we're talking about an anion, and that anion is the oxide ion. Notice that the oxide ion has a 2 minus charge. Let me show you again why that is. Here's oxygen. Element number 8. What's the nearest noble gas to oxygen? It's not helium, because helium, in order for it to be isoelectronic with helium, it would have to lose 1, 2, 3, 4, 5, 6 electrons. That's a lot of electrons. If it simply gained 1, 2 electrons, then it's going to be isoelectronic with neon. And that's why oxygen always forms that, or almost always forms that 2 minus. Exceptions, but we're not worried about those right now. Well, if I know that my electron configuration for oxygen, and I'm not talking about oxide, just plain old oxygen, is helium, which is the noble gas that precedes it, 2s2, 2p4. Well, if it gains 2 electrons, right, where are they going to go? They're going to go into the p orbital, because a p orbital can hold up to 6 electrons. That means that O2 minus is going to be helium, 2s2, 2p4, like that. Now, if I drop my 2s orbital, there's only one type of s orbital, isn't there? The 2s orbital, and then I have 1, 2, 3, 2p orbitals. Let's fill those up. In my 2s orbital, I have 2 electrons. In my, did I put the wrong number of electrons there? I did. This is supposed to be 2p6 because it gains 2 electrons. Okay, so in my p orbital, I should have 6. Let's fill them up. 1, 2. There's the 2 electrons in my 2s orbital. In my 2p orbital, or my 2p orbitals, I have a total of 6 electrons. 1, 2, 3, 4, 4, 5, 6, like that. And so the answer is going to be C. We have 1s2, which I left out. That comes from the helium. And we have 2s2 and 2p6. And you can see that all of the electrons have opposing spins, like that. Let me back up again. Did you notice something about the electron configurations of all of the ions on this page? Whether it's a sodium cation, calcium cation, an aluminum cation, a hydrogen, sorry, not that example, but a hydrogen anion, a fluorine anion, an oxygen anion, and nitrogen, right? My point is this, and what I was trying to get at is that every single ion that's shown on this page, they all have what in common? They all have a noble gas electron configuration, okay? Whether they're cations or anions, they always seek to gain or lose enough electrons to become isoelectronic with the nearest noble gas. That definition is shown right here, isoelectronic, and you need to know this definition. Isoelectronic means having the same number of electrons and hence the same ground state electron configuration. Look at sodium, okay? The sodium cation. The electron configuration of the sodium atom is neon, and then 3s1. If we lose that 3s electron, what does it simply become? Just neon, right? What if we look at aluminum? What's the electron configuration of aluminum, right? We have neon followed by 3s2, 3p1. Well, if I lose 3 electrons to become Al3+, you're going to lose the valence electrons. What's your electron configuration going to be? Simply neon, right? So the point is that all of these ions that you see here, the sodium cation, oxide, nitride, fluoride, all of these are isoelectronic with neon. That means they all have the same number of electrons, which is 10. all have 10 electrons, okay? They still are different elements, right? Because the number of electrons in an atom or an ion doesn't govern its identity, does it? The identity of an element is governed by the number of protons. Let's talk about the transition metals, which I told you going all the way back here. I kind of left the transition metals open and I said they're a little more difficult to predict, okay? Much more difficult to predict. Well, you need to be aware of a few of them. It says when a cation is formed from an atom of a transition metal, electrons are always removed first from the ns orbital and then from the n-1 d orbitals, not d orbitals, I should say d orbitals. Let's think about iron. Okay, if I write out the electron configuration of iron, let's go all the way back here. What's the noble gas that precedes iron? It's argon. So for iron, oops, didn't mean to do that. For iron, our electron configuration is going to be Fe. This electron configuration is argon, followed by 4s2, 3d6. Now, if we want to make an iron cation, because metals lose electrons, it might be a knee-jerk reaction for you to say, well, the last electrons that we put in when we wrote out that electron configuration were the d electrons, weren't they? So you might think, okay, well, if I'm going to form an Fe2 plus cation, you might think, okay, I'm going to remove these electrons first, but in fact, you don't. Okay, with a transition metal, you always start with the electrons from the ns orbital, which in this case would be a 4s, and then you go to the d orbital. Okay, it's it's a little bit counterintuitive, isn't it? All right, so if we look at manganese, for example, the electron configuration of manganese is argon 4s2 3d5. If you want to have a manganese 2 plus cation, you remove the s electrons first, like that. Okay, so always remove the s electrons first, and that is that's important that you know that. I want to go back here to my slide that has some, where am I? Nope. Let me back up. Go back to this periodic table here. Okay, there's a couple of elements that are transition metals, or near the transition metals, I should say, that only have one possible charge. And these are three exceptions that you need to know, okay? I'll tell them to you right now. It's zinc, cadmium, and silver. Again, I told you that group 2b, it technically isn't this transition metals. It's kind of all by itself, but you can think of it being a transition metal because it's close to the transition metals. Anyhow, zinc and cadmium always form 2+ cations, okay? So zinc is always 2+, no exceptions. Cadmium is always 2+, no exceptions. Now, silver is definitely a transition metal. And if you look at an element like copper, for example, well, we saw this in nomenclature that copper could be copper 1+, or it could be copper 2+. Also, if you look at iron, right? Iron, we just saw, could be iron 2+, or it could be iron 3+. Well, silver is unique in that silver can only ever be silver +1. Okay, and those are exceptions that you need to be fully aware of. A couple other exceptions that you should be aware of are chromium and copper when it comes to electron configurations. If you look at the electron configurations in here very carefully, you might notice something strange about chromium. Let's think about chromium for a second. The noble gas that precedes chromium is argon. What comes after argon? It would be 4s2, and then 3d, 1, 2, 3, 4. If you zoom in here, though, on the chromium, what do you see? It's 4s1, 3d5. So it's not what we wrote. Okay? So what happens is this is not correct. The correct way to write the electron configuration for chromium is this: argon 4s1, 3d5. Let me write out the orbitals and show you why. Here's the 4s orbital. Here are the 5 3d orbitals. So you'd have 1 in the 4s and 1, 2, 3, 4, 5 in here. Okay? If it was the first way, 4s2, 3d4, well, I mean, you can draw exactly what it would look like. It would look like this. And that is actually less stable than if you take that 4s electron and you put it up in the 3d orbital like that. The reason why chromium has this electron configuration is because there's an inherent stability with either having a set of orbitals completely filled or half filled. And so you can see that in this case, the 4s is half filled and the 3d is half filled. There is another exception to this, or there is another exception, and that's copper. Okay, if we write out the electron configuration, I'm kind of running out of space here, but we'll just write it quickly here. Copper, the noble gas that precedes copper is argon, and so we would have 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. But in fact, if you zoom in, what do you see for copper? It's 4s1, 3d10. And the rationale is the exact same as the rationale for the chromium exception. Okay, is that it's actually argon 4s1, 3d10. Because when you have this electron configuration, the 4s orbital is half filled and the 3d orbital is completely filled. Whereas in the first one that I have the X gone through, the 4s is completely filled, but the d orbitals are neither completely nor half filled. And so this is more stable. Now, if you've been paying close attention, you might remember me, yammering on about this quite a bit at the beginning of the lecture, that elements that are in the same group or family share the same characteristics. In fact, if you look at molybdenum, which comes right below chromium, you'll see that molybdenum has that same thing where it goes 5s145, whereas tungsten, which is element number 74, the W stands for wolfram or tungsten is what we call it. It says 6s2, 5d4. So you see that that exception or that rule doesn't hold true for tungsten. Let's look below copper. You can see that silver follows the same rule as does gold. So it's kind of weird in a way that the rule applies to chromium, molybdenum, not tungsten. Okay, it applies to copper, silver, and gold. Anyhow, and if you're wondering, those are some pretty weird exceptions, Mr. Dion. Do I have to know those? The answer is absolutely yes, because I've done the ACS, or I've looked at enough ACS final exams to know that they like to ask those exceptions. Okay, let's move on to a new subject, and this subject is called effective nuclear charge. Think about what it's, what this term might mean. We know that in the nucleus, right, of an atom, we know there's a charge because there are protons and neutrons in a nucleus, and protons have a positive charge. Now, what it means by effective nuclear charges, what about those electrons that are outside of the nucleus? They do feel the positive charge of the protons, but what we're going to see is that not every electron feels the full effect of all of the protons in the nucleus. And so the nuclear charge that an electron feels, we call that the effective nuclear charge. Okay, here's the definition laid out for you maybe a little more clearly. Effective nuclear charge, which we abbreviate as ZEFF, is the positive charge felt by an electron. The way that you calculate effective nuclear charge is shown right here. Effective nuclear charge is the atomic number subtract the atomic number minus sigma. Now, sigma is called the shielding constant. Now, actually looking at the values of the shielding constant is a little bit beyond the scope of our class, but there's a very close approximation that you can calculate literally on your fingers to give you the effective nuclear charge. And that is shown right here. It says that effective nuclear charge is approximately equal to atomic number subtract the number of inner or core electrons. Right? If we look at the electron configuration of sodium, We'll do this kind of quickly. It's 1s2, 2s2, 2p6, 3s1. What are the core electrons? Anything that's not a valence electron, which is the electrons with the highest principal quantum number for a representative element, those are considered core electrons. So all of these electrons here, these are core, right? How many are there total? 1s2, that's 2. 2s2, 2 plus 2 is 4, plus 6 from the p gives me a total of 10. And so sodium has a total number of electrons, or an atomic number of 11, but it has 10 core electrons. And if we use this formula right here, 11 minus 10 gives you an effective nuclear charge of 1. This is the effective nuclear charge felt by that 3s1 electron. We're not going to do this for all these, but if we look at magnesium, the same thing applies. 1s2, 2s2, 2p6, 3s2. These are the core electrons. There are 10 of them. How many valence electrons do we have? We have 2, and the total number of electrons, or our atomic number, is 12. 12 minus 10 is 2, and so the effective nuclear charge is 2 for those valence electrons of magnesium. What's the trend that we see here in this table? Well, the trend is this. As we go from sodium to magnesium to aluminum to silicon, these are all elements that are found in period 3. Period 3 elements. What do you notice? You notice that as we go from left to right in the third period, and we're going to see that it's true for any period, as we go from left to right, effective nuclear charge increases. What do we see the effect of the atomic radius is? It decreases. Okay, so as we go across a period from sodium to magnesium to aluminum to silicon, then to phosphorus, sulfur, chlorine, and argon, we see that as we go from left to right across a period on the periodic table, the radius of the atom, the size of the atom actually decreases. Now, the first time I heard that, I thought it was counterintuitive because I said, well, if we're increasing the atomic number, aren't we increasing the amount of matter? And matter takes up space, doesn't it? We're increasing the number of electrons, and we're increasing the number of protons and neutrons. So we keep adding matter as we're going across the period. Why wouldn't the element get bigger and bigger? Well, again, the rationale is based on effective nuclear charge. In an atom, we know that there's an electrostatic interaction, right, positive and negative, between the electrons, which are negative, and the protons, which are positive, in the nucleus, right? Positive and negative attract, opposites attract. We know that. In multi-electron atoms, though, so anything that's not a hydrogen atom, or an ion that has only one electron, I should say, the electrons do not experience the total attractive force of the nucleus. The attractive force experienced by an electron in an atom is referred to as the effective nuclear charge. Now, I have many slides here in this deck that rehash the same concept. And the reason why is because later on, we're going to look at new concepts like ionization energy, electron affinity, and all of those concepts that we're going to see in the rest of the chapter can all be based on or explained with a firm understanding or a good grasp of effective nuclear charge. Let me give you kind of Mr. Dion's one of his ways of explaining this. Okay, if you think about the lithium element, okay, lithium is element number 3. So in the nucleus of lithium, there are 3 protons. Maybe we could put +1, +1, and +1. There's the nucleus of a lithium atom. Okay, here's the nucleus. Well, we know that the electron configuration is 1s2, 2s2. So we have a 1s orbital. In that 1s orbital, we have 2 electrons. I'm just placing them anywhere. And then in the 2s orbital, sorry, I can't draw a circle very well, can I? We have 1 electron. Well, if you think about that valence electron, does that valence electron feel the force or the attraction of all 3 of those protons in there? The answer is no. Why is that? Because there's 2 electrons in the 1s orbital that are blocking it or shielding it from the nucleus. If we think about a beryllium atom, okay, so if we go from lithium and then we just go to the next element, which is beryllium, 1s2, 2s2. Well, since the atomic number of beryllium is 4, it's going to have 4 protons in the nucleus. Still got a 1s orbital with 2 electrons in it, but now the 2s orbital has 2 electrons in it like that. Well, why is the beryllium atom going to be smaller than a lithium atom, even though it's got more matter? Well, let's think about it. Both of those valence electrons are going to feel more of the force of that nucleus. Now, why would that be? Because I still only have 2 core electrons, right? Before I had those 2 core electrons, and they could both take care of this guy, right? They were both shielding the same damn electron, pardon my language. Whereas in beryllium, you got 2 core electrons, but now they've got to shield 2. They can't shield 2 electrons as effectively. And so the outer electrons, those valence electrons, are going to feel more of the effect of those positively charged protons in that nucleus, and that's going to pull them in tighter. Now, obviously, my sketch is not to scale, and I'm actually going to skip ahead a little bit. I want to show you, where is it? Down here, okay? If you look at the size of atoms, as you go from lithium to beryllium, what do you see? The size of the atom decreases. You go from boron to carbon, so on and so forth. They keep decreasing as you go across the period. And again, that's because effective nuclear charge increases. Now, I have some more slides here that go over effective nuclear charge in even more detail. Let's see if we can make some sense of these to further our understanding, or our grasp, I should say, of effective nuclear charge. Think about an electron in an atom. It's attracted by the nucleus, isn't it? Because the nucleus is positive and an electron is negative. Well, it's also repelled by the other electrons in the atom. For example, if we go back to my beryllium, these 2 electrons are going to be repelling each other, aren't they? Absolutely they are. The inner shell electrons, or the core, right? This is the same thing as the core electrons. They're going to reduce the nucleus attractive force felt by the outer electrons, and that effect is called shielding, right? They're blocking it. Here's a figure taken from our book. It says here that electrons that are in the 1s orbital cancel some of the attractive force felt by an electron in the 2s orbital. The 2s electrons in the 2s do not shield electrons in the 1s orbital. Okay, so it's only inner electrons that shield outer electrons. The shielding thus reduces the attractive force between an electron and the nucleus, and the reduced attractive force, termed effective nuclear charge, is calculated as such. So we have the effective nuclear charge, which is the attractive force experienced by an electron, and the actual, which would be the full attractive force of the nucleus. That's only based on the number of protons. Well, again, if we use the formula that we saw before, which is effective nuclear charge is pretty much equal to atomic number minus the number of core electrons, we see that as we go across a period from left to right, that effective nuclear charge is going to increase. Now, I'm not going to talk about the effective nuclear charge increasing going down a group a lot. The book mentions it in a little more detail. But even though effective nuclear charge does increase as you go down a family or a group, you might think, okay, well, what you just told me is that as effective nuclear charge increases, that the size of an atom is going to decrease. That's only for periods, okay? So increasing effective nuclear charge, decreasing size. And that's because effective nuclear charge is the dominant effect. When we go down a group, even though effective nuclear charge is increasing, we see that we get increasing size. And the reason why is because effective nuclear charge is not the dominating effect. It's the fact that the principal quantum number is increasing as you go from 1 to 2 to 3 to 4, and you're adding electrons to a bigger valence shell. And so that's why when you go down a group, the size of an atom increases. Effective nuclear charge increases somewhat going down a column or a family or a group. However, because the valence electrons are now added to a shell with a higher principal quantum number, a higher n, the electrostatic interaction or attraction between the nucleus and the valence electrons actually decreases, and therefore size increases. Okay, whereas going across a row or a period, the nuclear charge increases faster than the shielding. And so as we go across a period, the number of protons is increasing, but the number of core electrons is not changing, is it? And so the electrons that are the valence electrons are going to be pulled in tighter and tighter and tighter because the nucleus is getting bigger, more positively charged, but you get the same old number of shielding electrons. The size of an atom, which I keep referring to in this lecture, is actually difficult to define. We talked about the shapes of orbitals in the last chapter. We talked about an s orbital as being a sphere, and then we talked about a p orbital as being a p for a peanut or a propeller, whatever. Well, again, when we looked at the shape of an orbital in the last chapter, we said the outer boundaries of an orbital are actually not that well defined. When we draw the shape of an s orbital or a p orbital, what we're saying is that's where we have a 90% probability of finding an electron. And so size is actually directly related to 90% of where the electron density is found around the nucleus. So a covalent atomic radius is actually defined as half the distance between the two nuclei of two identical atoms covalently bonded together. Let's say, for example, you have chlorine, right? Chlorine gas, which is Cl2. If you look at a molecule of chlorine, when you measure the distance between the two nuclei, you find that it's 198 picometers. And so if we divide that distance between the two nuclei in half, we get 99. 198 divided by 2 gives you 99. And so that is the atomic radius of a single chlorine atom. You see, the same thing applies to a carbon-carbon bond, the same thing applies to a carbon-carbon bond. So we know the distance between the two atoms in a carbon-carbon bond is 154 picometers. We divide that in half, and we get the atomic radius of the carbon atom. So here, in these first two examples, we define the atomic radii of chlorine and carbon. So when it comes time to predict the length or the bond length between these two elements, carbon and chlorine, right, which we see all the time in organic chemistry, how do you predict that bond length? Well, you take the radii of each of the atoms and you simply add them together. And so this is where bond lengths come from, if you've ever wondered. Again, this slide here shows you the trend for the size of atomic radii in the periodic table. And what do we know? We know that the size of the atomic radius increases going down a group or a column. Why is that? Because we increased the principal quantum number as we go down a group. And as principal quantum number increases, the orbitals get bigger and bigger and bigger, right? We're going from 1s to a 2s to a 3s to a 4s to a 5s to a 6s for all of these elements here. So it makes sense that in group 1, the elements keep increasing. Again, as we go across a period, right, effective nuclear charge increases, therefore size decreases. And the last thing I'll leave you with this evening before we head out to the lab is that you probably noticed that there's some anomalies here, right? You might be thinking, well, come on, around the transition metals, I'm not seeing a big change here, okay? If I look at the transition metals here and I look down here, I'm not seeing a big change. Well, remember, if you read the introduction to this chapter, it's called Periodic Relationships Among the Elements. Another way you could say this is periodic trends among the elements. The name of the chapter wasn't periodic rules carved in stone that there's no exceptions to. Okay, we're just looking in general terms. And generally speaking, as you go from left to right across the period, atomic size decreases. And definitely as you go down a group or a column or a family, whatever you want to call it, atomic size increases.